Section 24.7 Molecular Structure and Energy Levels from Computational Chemistry. It is possible to use a computational chemistry software to calculate the molecular orbital coefficients and the molecular orbital energy for a molecule. For example, over here we're looking at the symmetry-adapted canonical MOs of formaldehyde. This molecule belongs to C2V, the C2V point group. In the C2V point group, there are four different irreducible representations: A1, A2, B1, B2. There are also four symmetry classes that include the identity symmetry element, the C2 rotational symmetry element, and there are two different sigma V symmetry elements. Both sigma V's contain the rotational C2 axis, but one is perpendicular to this molecule. One contains this molecule. Now let's look at the MOs. I'm going to talk about this MOs from the lowest energy to the highest energy, or you can say from the most negative energy to the most positive energy. So first, this 1A1, that means totally symmetric with respect to all different symmetry operations. So if you do identity, rotation, reflections, there's no sign change to the phase of this MO. This MO looks like it's localized on one atom. Well, that's not 100% precise statement. It looks localized on oxygen only because the energy of this 1s orbital centered on oxygen lies much lower than all other atomic orbitals. So that means the interference between this 1s orbital on oxygen and any other atomic orbital is minimal. So still, you need to imagine this MO is delocalized over the whole molecule. It's just the coefficients, the MO coefficients on carbon and on hydrogen atoms are so small we cannot see those on this picture. This is the 1s orbital of carbon. So this guy has lower energy than this guy only because the 1s electrons in the oxygen atom feels attraction from 8 protons. Over here, only 6 protons in carbon. All right. Of course, there's electron shielding. I think it's about 0.3 from the other 1s electrons. So the effective nuclear charge here is roughly 7.7. Over here, the effective nuclear charge is 5.7. So that means this 1s electrons feels more attraction, less attraction. And anyway, chemists do not care about core electrons or core orbitals. Okay, now this is more interesting. This is 3A1. Oh, by the way, this is A1 symmetry, A1 symmetry, A1 symmetry. So to distinguish this 3A1 symmetries, we say this is the first A1, the second A1, and the third A1. This is also symmetric with respect to all four different symmetry operations. This is apparently delocalized over the whole molecule, but mostly it's here. This is the interaction between the 2s orbital here and the 2s orbital here. This is constructive interference. So mostly it's carbon-oxygen sigma bonding orbital with A1 symmetry. This one, this is also sigma bonding. It's also symmetric. So you can see this is A1 symmetry. That means this MO is symmetric with respect to all four symmetry operations. The first one doing nothing. The second one is rotation. The third and fourth are both reflections with respect to the two sigma V symmetry planes. So this one is sigma bonding mostly between carbon and hydrogen, carbon and hydrogen. I would consider this part as lone pair electrons on top of oxygen. Finally, we have a different irreducible representation here. It's a B2. B means when you rotate this MO, the sign changes. So I want you to imagine this C2 principal axis here that crosses the oxygen and carbon, and then if you rotate this MO 180 degrees, the sign changes. Okay, this red lobe will be here, the blue will be here. Alright, so A and B are referring to the symmetry and anti-symmetry with respect to rotation. 1 and 2 are referring to the symmetry and anti-symmetry with respect to the reflection. Alright, so now I want you to imagine there's a sigma V over here that is perpendicular to your screen. Alright, and then if you do a reflection, the sign of the MO changes. Alright, so that's why it's a B2 symmetry. Alright. I forgot to talk about the nature of the bond. This is obviously a sigma bond between carbon and this hydrogen. Another sigma bond between this carbon and this hydrogen. And also, I think there's a little bit pi weight. Yeah, it does look like a little bit pi character here. So you have a P here on carbon, another P orbital on oxygen. All right. So it tells us it's possible. I think it's possible to have this pi bonding orbital between carbon and oxygen interact with these two sigma bonding orbitals. Now let's look at this one. A1 symmetry, completely symmetric with respect to rotation and reflection. Now if you look at this, this is a little bit hard to analyze. There's a constructive interference between these two hydrogen atoms. All right, but you know, if you took general chemistry and organic chemistry, you know there shouldn't be any bond between these two hydrogen atoms. But by looking at this, I want to say you can say there's a really weak constructive interference between this 1s orbital and this 1s orbital. I wouldn't call that bond because these two hydrogen atoms are really far away from each other. So this constructive interference is minimal. I think in this picture, I think they choose a ISO value for plotting the MO that this is kind of overly presented over here. Right here between carbon and oxygen, I think this is constructive interference, so there's some sigma bonding between carbon and oxygen, and this part I would say it's lone pair. B1 symmetry, again B means rotation, so if you rotate this, the sign changes. The red will go left, the blue will go right. 1 means it's going to be symmetric with respect to the sigma V symmetry plane that's perpendicular to this molecule. B2, this one looks like sigma bonding, and then pi anti-bonding. So it looks like pi star anti-bonding here between carbon and oxygen, but between this carbon and this hydrogen, it's sigma bonding. So it's kind of a mix of anti-bonding here and bonding here. This symmetry is B2. B means it's anti-symmetric with respect to rotation. 2 means it's anti-symmetric with respect to the symmetry plane, sigma V plane here. That's perpendicular to this molecule. Finally, this is an electrostatic potential surface. The definition of this is you just need to imagine there's a +1 test charge, and you put it here, you feel overall attraction, and the attraction energy divided by the charge of the tested charge. That will give you the electrostatic potential in volt. So I think it's negative here, it's positive here, it's positive here. Blue is positive, red is negative.